Steinhauer here, welcome back. Thought I'd begin today's class with a review question to go over and remind ourselves what we were talking about in the last video. So here it is. Halo stars on average are what than disk stars? Older and more metal rich, younger and more metal rich, older and less metal rich, or younger and less metal rich? So you can certainly make a guess. Let's talk about this though. If you recall, the Milky Way looks something like this. You've got a nice thin disk, you've got a little bulge in the middle, and the halo is that region of the galaxy that extends actually well beyond the disk in kind of a spherical sense. And the way the Milky Way we think formed is these objects in the halo formed first. And so these are the oldest stars in the galaxy, those stars in the halo. And we think that all present star formation happens in the disk of the galaxy. This is where we have bright blue stars and where we have emission nebulas and present star formation. All of that is only occurring right now in the disk of the galaxy. And so while there are old stars also in the disk of the galaxy, all of the new stars, all of the young stars are in the disk of the galaxy. As far as metal abundance, and by metals, astronomers really mean everything heavier than hydrogen and helium, but certainly iron and things like that count. Remember, this is also an age indication, in that the first stars that formed, the oldest stars in the galaxy, should have none of these metals in them. They should have been formed with entirely hydrogen and helium. And while those stars will be converting heavy elements in their cores, those cores won't be visible to us. So we won't be able to detect that change in abundance. But as supernovas go off and these metals and heavier elements are formed, they enrich the galaxy. They enrich the material in the galaxy. And the next generation of stars that form have more metals, and subsequent generations just have more and more metals. So we expect the younger a star is, the more recently it's formed, the more of these generations will have passed, the more metal rich those clusters will be, and those are all in the disk of the galaxy. So we expect disk stars to be younger and more metal rich than halo stars, but this question asks it in the opposite direction. Halo stars on average are older and less metal rich than their disk counterparts. Okay. The next slide, I've got a still from a video that I posted in the supplemental materials below that, again, talks about how, or at least shows how galactic formation happens, shows a potential scenario for the Milky Way forming. And just like stars forming, galaxies forming are much more complex than just a giant cloud of gas condensing into a galaxy. All galaxies, including our own galaxy, assuredly is built up from many smaller galaxies that have merged. And then when you get a big galaxy, it continues to cannibalize smaller galaxies and incorporate them into its mass. So when we say that halo stars form first and then disk stars form later, that's kind of a simplification of the true process that's happening. I encourage you to watch the video and take a look at how that works. It's fascinating and cool and fun to watch. Okay, our next topic is we need to figure out how massive the Milky Way is, and this leads us into some exciting new results in astronomy and interesting and fascinating and really cool results. So let's first think about how we can measure the mass of the galaxy. Obviously, we don't have a scale. We can't just put it on something to measure its mass directly. We have to use the observations of the things that are in the galaxy to infer what the mass of the Milky Way must be. And we can use the fact that we know that the more massive something is, the faster something will orbit around it at a given distance. And so if you may remember, the escape velocity formula that we talked about with both at the beginning of the semester and with black holes is the escape velocity squared is 2 times g times the mass of the thing you're trying to escape from divided by the distance from the center of that thing. The circular orbit velocity is a very similar concept. This is how fast you have to be moving to orbit something in a perfect circle. And it's very similar to the escape velocity formula. The circular velocity squared is gm over r. In fact, it's just missing that factor of 2 here in calculating the circular velocity, orbital velocity with the escape velocity. And this is important because if we can measure how fast stars are moving in circular orbits around the Milky Way at a given distance, we can calculate the mass. And that is, in fact, how it's done. So let's solve this equation for m. Let's just do it here. We can multiply both sides by r and divide by g. That over here will cancel out the r's and the g's, and we'll be left with the equation that I'm going to write down on the next slide, which is m equals r times v squared over g, where v is the orbital speed for an object moving in a circular orbit, r is the distance from the center of the galaxy, and m of r is the mass of the galaxy. Now, it's not the entire mass of the galaxy. This is a little bit interesting. If we look down on the disk of the Milky Way, it looks something like this, and you got some spiral arms and whatever. I'm drawing this pretty badly, I apologize. Anyway, if you say, I want to measure, you got some star here and it's moving in a circular orbit, let's say around the galaxy, and I want to measure, I measure the velocity of this star, and I know how far it is away, and I know how fast it's moving around the galaxy. I can use those two to calculate this MR. This MR, this little subscript R, means it is only the mass that's interior to that orbit that you are measuring. It's an interesting fact that if you have a spherical distribution of matter, these equations work perfectly to give you all of the mass inside of that orbit and ignores all of the mass outside of that orbit. So that's what this subscript R means, the mass within that orbit. But this not only gives us a chance to measure the mass, total mass of the galaxy, it gives us a chance to measure the mass distribution of the galaxy. If we can measure the velocities of stars at lots of radii, we can get the mass interior to all of those radii and see how the mass is not only of the whole galaxy, but how it's distributed throughout the galaxy. And that's useful. Okay, so let's do this. What is the mass of the galaxy inside the sun's orbit? Well, we need to know some numbers first. We need to know, first of all, that r, the distance from the center of the galaxy, is about 28,000 light years. We need to know how many meters there are in a light year. There are 9.46 or so times 10 to the 15 meters in 1 light year. So those cancel out. And if I multiply those two numbers together, I get 2.65 times 10 to the 20 meters. That's how many meters it is from us to the center of the galaxy. It's a lot of meters. How fast are we moving about the galaxy? This is a number that's been measured, and the velocity turns out to be 220 kilometers per second. It turns out that's pretty much the orbit. Oops, I forgot a zero there. 220 kilometers per second. It turns out that that's the orbital speed at a lot of different distances, but we'll talk about that shortly. Now, again, we're going to want meters here, so we can multiply by 1,000 meters in a kilometer. Kilometers and meters cancel out. Kilometers and kilometers cancel out, and that is 220,000 meters per second. Speed we're orbiting the galaxy. Of course, we know what g is. It's 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. And so we can plug all of this stuff in. M equals r 2.65 times 10 to the 20 meters times v squared, 220,000 meters per second quantity squared, divided by g, 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. Great. Throw all that into your calculator, and you're going to get a number that is 1.92 or so times 10 to the 41. Okay, that's a really big number. What are the units on this number? We can probably work it out here. We've got a meters per second quantity squared here. The meters squared, the second squared cancels that second squared. You've got a meter squared and a meter up here, canceling the meters cubed down here. And you've got a kilograms in the denominator of the denominator. So that moves up to the numerator, and this just becomes kilograms. That's a lot of kilograms. But this isn't surprising. We're talking about the mass of the galaxy. There are billions of stars in our galaxy. It's not surprising this is a big number. It might be more useful to know how many solar masses of material this is. Let's do the unit conversion. We know that 1 M sun is 2 times 10 to the 30th kilograms. So that'll cancel out our kilograms. If we divide this by 2 times 10 to the 30, we get a number that is 9.6 times 10 to the 10 solar masses, which is pretty darn close to 10 times 10 to the solar masses, which is 10 to the 11 solar masses. 10 to the 11 solar masses. That's 100 billion solar masses. And we think that most stars are less massive than the sun. So that's hundreds of billions of stars just within our orbit of the Milky Way galaxy. So when you hear somebody like Carl Sagan saying there are billions and billions of stars in the galaxy, we know that because we can physically measure the mass of the galaxy using these simple equations. Okay, we'll talk about in the next video some implications of this mass, other ways we can get information about the galaxy. See you then.